let's carry on our conversation about these confidence intervals, and let's make it a little more powerful. Recall that last time we talked about our error rate for a confidence interval, and our error rate was the ZC, the Z confidence level number that we needed to get whatever percent confidence we wanted in our Z curve, divided by standard error, sigma divided by square root of n. And one of the points that I made towards the end of the last time was you should be a little suspicious of this, because how could we possibly know sigma if we didn't know mu? Remember, we were using x bar as a point estimator to estimate mu. And yet somehow we knew sigma. Well, there's plenty of cases where this might be true. You could know a lot about a population level of variance, just not information about that specific population. For example, maybe blood pressure. I know a lot about how blood pressure deviates all over the world. It's a very cheap thing to measure. But maybe I'm making a specific population and mu is, let's say, all the people in Texas. So suddenly I'm curious, is that average just in Texas maybe a little different than the rest of the world? Since there's still people, I would imagine sigma might be the same, possibly the mu's different. Possibly. However, if it's not, that's okay, because we can make some changes. If you don't know what sigma is, a great point estimator for sigma would be the sample deviation, S. In fact, you see us make this change here today, where we're trying to talk about sample deviations, because we're trying to get ourselves a little bit away from this idea that maybe I know all sorts of information about my data. If I make this change from sigma to S, from population deviation to sample deviation, I can't use ZC scores anymore. Instead, I have to introduce a new thing that we call a TC score. So we introduce the student T distribution. It is a thing that we can use. It's very similar to the ZC scores. It's very similar to the Z scores under the normal curve, but you don't quite have a normal curve. So here's what a student T distribution looks like. Just like Z score, T scores are symmetric around a standardized zero. That's where the mean should live. They're bell-shaped, just like the normal curve. As the number of items in our sample gets large, I've written this as it goes to infinity, but of course it won't quite reach there, but as we get lots of sample points, maybe 1,000 or 50,000 or 15 million, then the T curve starts to look more and more like the Z curve. It flattens out a little bit, it has less of a poof here, and at the sides, the tails, which in the T distribution we allow to be a little bit thicker and a little more separate from the x-axis, those kind of come down and it starts to take on that normal curve shape, which if you take one of my calculus classes you might know is called a Gaussian curve shape. So symmetric around zero just like before, bell shape slash normal just like before. It's not quite normal, it's a little bit raised. Still, as we get more items in our sample size, the t-score starts to look like the z-score. So think of it as a rougher z-score. Partial check. And the area under the curve, as usual, is going to be 1. But all we have to really do is get some sort of error compensator for this idea that since we don't have a lot of data, we don't have in population level like we do for the z's, that we're going to be a little bit rougher, and we can cope with this idea by talking about what we call degrees of freedom. So let's talk about degrees of freedom. Degrees of freedom is this. The formula for degrees of freedom is n minus 1. Remember, n is sample size. So number of people in your sample, you get rid of 1, and n minus 1 is your degrees of freedom. Maybe a simple way to talk about degrees of freedom is this. Let's think of an example. Let's suppose that you want to average, let's say you're taking a class in biology, and in this bio class you have 4 tests. Test 1, Test 2, Test 3, and Test 4. And if you add those 4 tests together and divide by 4, that should be your class average for the tests, right? This bio class, their tests, all of the tests are equally weighted, all that good stuff. Let's say you would like that average to be 90%, 0.9. Now, of course, you'd probably be willing to take 90% or higher, but let's pretend you want it to be exactly 90%. Degrees of freedom is this. When you've got 4 numbers here to choose from, you can score whatever you want on your first test. Doesn't matter. Let's say you score 0. That's okay. You can score whatever you want on your second test. Maybe you score 100. Your running average might be 50 about now, but that's fine. You can score whatever you like on your third test. Who cares? 80. However, if you want to make a 90%, now you have to figure out what you score on your fourth test. That is your last test, and that one isn't free anymore. Right? You could score whatever you want on these, but if we want the average of these scores to equal 90, we're going to have to figure out a number to plug in here. And that number better add to these ones and give us 90 when divided by 4. And in fact, we might decide that with a 0 right here, this number might even have to be pretty large. Let's make it a more extreme example. You could do whatever you wanted. You said, I'm free. I'm free on the first test. I can do whatever I want on the second test and the third test as well. Zeros all the way down. You and I know that you can't make more than 100% on a test. So this last one's not free, and in fact, for this to work, you're going to have pretty close to 400 in here, right? I don't know, 300, whatever 9 times 4 is, 360, I guess? We know that can't happen, but when we talk about degrees of freedom, we don't care about what's a possible test score. We just care about which ones are free and which ones aren't. So, when we're talking about degrees of freedom, it's n-1 because all the other people in the group can kind of do whatever they want, but if you're imagining that you have some fixed x bar at the end that you're getting to, that last one suddenly gets kind of locked into place by the craziness the other ones are doing. Now, of course, if they're doing really crazy stuff like this, we're not really expecting a normal curve, so we don't normally see this extreme of an example, right? We're just seeing that last piece isn't quite free. So what we want to do is we basically want to revisit the problem we were looking at last time. Last time we had looked at this and I said we happen to know the population sigma. But let's say we didn't. Let's say there hadn't been a U.S. Census recently. Just because we haven't had a U.S. Census doesn't mean the statistics can't help us. So let's recalculate the family income in Victoria, Texas, circa 2010, with my data that I've got from 2010 right here. Same data as before, but this time we're going to pretend like there wasn't a census. We don't know. Just because I don't know what the actual population numbers are, remember we looked last time what it was, about 42K? That happens to be the case. We'll use that here as a check, but the fact is I don't have to know to still get myself a 95% confidence interval and decide that I am 95% of the time that I build this, I will actually have the population mu captured in this range. So let's take a look at how this works out. The exact same process. This actually leads to an interesting set of things. Namely, it's going to be your job, particularly as we look towards the final exam, to be able to read a problem and decide which of these 2 confidence intervals should I do. If they say the magic words, find a confidence interval, you know you're going to find a confidence interval, but you have to decide. Should you use the z-score formula from last time, or should you use the TC-score formula for student t-distribution? Well, part of that's going to depend on, did they give you information about population deviation sigma, or did they give you only information about sample deviation s? And in this case, they haven't even told us x bar or s. Instead, they've given us raw data. But this is sample data. I've gone ahead and labeled this sample data for you. But if we're asked, find a 95% CI for the data, that is a perfectly legitimate thing that we would be asked to do. And I can tell you, Just looking at this, since I know that this is family salaries in Victoria, Texas, circa 2010, this is not population data. There's only 10. We know there's about 13,000 families in the Victoria area. So it doesn't make sense that we would have any population information here if on the board is all the knowledge we've got. Start to get your sort ability good. Be able to look at the problems in one section and see, ah yes, these clearly do give me sigma. Be able to look at the problems in another section and say, no, they don't give me sigma. Remember, on the final, you're going to get a problem. I'm not going to ask you both. You're going to have to read a problem and decide, is it sigma or is it S? Is it z-scores or is it t-scores? How can you make that decision? So there's two aspects of this stats business. Aspect one, can you do the mechanical calculations once you're told exactly what to do? Well, that's great and that's very important. But aspect two, and this is a much harder thing to do, are you able to look at a random word problem and decide, these are the calculations I should do? I see those as two very separate problems. I can walk you through the calculation steps. It's the decision process of how you read a problem and figure out which of the many things you could do is the right one to do. That's a lot more complicated. And just as an observation, I do consult for statistics in public, and people hire me to do statistic consultations. Many times I find myself doing very simple tests that we actually talk about in this class. I know it's an intro stats class, but I promise you this is useful stuff that I get paid good money to talk to people about. They're not paying me for my ability to do these calculations. Yes, they expect them done, but the mechanical side's not very profitable. It's the decision side. It's the fact that I can say, yes, this is the test we want, here's why. So, here, yes, t-test is the test we want for student t-distribution to find this confidence interval because I only have sample data, and that means I only have access to the sample deviation. I can't tell you about a z-score because I don't have sigma. There's no way to find sigma on this board. All right. We've already entered the data in our calculator, and our calculator does have a stored memory, so I'm just going to go back. Let me show you again how that works. You hit second, and you hit data, and you go back to one variable statistics, and again you pick your same frequencies as before, and you can get yourself back to your, you don't hit the enter sign quite as many times as I did, you can get yourself back to your data. Remember, x bar for us was 36,129.8. And if you go right down on your calculator to the third level, it has calculated out S for you. Notice if you go down to the fourth level, it's tried to calculate sigma, and notice this sigma is not the sigma we used before. That's because your calculator's not magic. It's not calculating the population sigma. Remember, S and sigma have two different formulas. One divides by capital N, the other divides by n minus 1. So your calculator, since it never knows if you're giving it sample or population data, it simply calculates both, and it's your job to look at these and say, ah, we have sample data, I'm going to trust the SX. S equals 14775.4386. In real life, I would recommend using a memory storage feature on your calculator to make sure that you're not rounding too early. You want to round only at the very end. Okay, to make this calculation work, we would like to build a confidence interval around where we think mu should live. That confidence interval is going to have x bar plus error and x bar minus our error. Notice this is the same formula as last time because the idea hasn't changed. The algorithm's perfectly fine. What has changed is what E is, because we don't have as much information. I'm not giving you as much insight as I did last time. We're in a less data-rich environment. Still, x bar is the same, 36129.8, 36129.8. We just have to calculate E. And E involves TC divided by S, which we just calculated here as 14775.43864. Divided by square root of n, which is still square root of 10. But now, instead of looking up a z-c score, which I showed how to do last time on a normal curve, we have to look up a tc score, And we have to do that on a student's t-distribution. To successfully look up TC scores, you've got to get the right chart. It's called Critical Values for Students' T-Distribution. Looking something like so. And you have to successfully know degrees of freedom. There are 10 things in my sample size, so there are 9 degrees of freedom for us. We would like to find this with a 95% confidence level. So you go to a TC chart. This is a pretty standard chart here. There will usually be a lot of headings on the tops of one of those charts. You're currently interested in just C. C for confidence level. You go down to the 95 column, 0.95, because we wanted a 95% confidence interval. So you go to this 0.95 column here on the C row. Ignore the rows above it. We're not doing one or two-tailed yet. And you need to go down until you find where you have 9 degrees of freedom. And if I follow 9 degrees of freedom over to the 0.95 column, I'm getting 2.262. That is your T-score. TC equals 2.262. Down here I've written, just like we had the Z-score, here's the T-score, but we're looking at the TC value, and so this is what we've got right here. So TC is 2.262. Your ebook has videos attached to it that do more calculations than this one. I only ever do about one calculation myself, but that's okay. We've got this calculation here. We can go ahead and make that calculation actually happen. 2.262. Let me type this in here. 2.2, and I'm going to go ahead and clear actually. 2.262 times fraction bar. I want to put 14,775. So I get 14,775.43864. Again, the more accuracy you can get there from your calculator, you want to round at the end all over the square root of 10. Hit enter. I've got myself a number here. Let me go ahead and pop that on the board for E. 10,568.977. 10,568.977, all right. Plus, minus 10,568.9777. And of course here, let me squeeze this in, plus E. We'll call it E for a second, you know what I mean. All right. If I take this number and subtract it from 36,129.8 minus 10,568.9777, I get 25,560.8, less than mu. Is less than, I also get 36,129.8 plus 10,568.977. 46,698.777, rounded to 78 for pennies. We've calculated a T-score. Some things to notice about a T-score. A T-score tends to be a little bit less accurate than a Z-score, because we don't have information about the population deviation. A big thing that changed here, and this is something to watch out for in your data. When I told you about population, I told you that it turned out that the population variance was 19 squared, 19,000 squared, so the population deviation was 19,000. That was a very large amount of sigma here when we had the sigmas back for our E. And so we ended up having a larger number here for E than we ended up having this time. That has to do with how turbulent our random data is. If you look at our random data, it's actually not very turbulent. There does happen to be this 2396, but other than that, our data seems pretty solid here. It's not all that wiggly. So you can get some interesting insight, I think, in between the calculations of the two. Oftentimes, if you have population measurement, you tend to think of you having some more precision, because you tend to think that the population measure is going to use a z-score. And notice the difference in the numbers we multiply. We used, what, 1.96, I think, as our ZC last time? This time here, we had to use 2.262. So we multiplied by a much bigger number and expected that to stretch the goalposts wider. However, we had a much less variable sample than the sigma that I talked about before. Extraordinarily so, really. The difference between 14K, almost 15K, and 19K is actually lots of Ks. So you can find that there's maybe a little bit of difference when you calculate out these numbers, and looking at those can give you some insight into how turbulent your data set is. This data set is actually pretty much very well clustered around the normal, and that's actually to be expected because I generated this using some random number generators around where I knew the population calculations to be, around that 42K. So these guys happen to be pretty close. If I picked a new random sample, I would expect a new range here. But nonetheless, this range again is a range that I am fairly certain actually is going to have the right stuff. I am getting pretty much out of time, so this is the calculation way. Notice the difference. If you've got sigmas, you use ZC scores. If you've got standard deviation S, you have to use TC. Notice it's the same formula though, minus E plus E. Next time we're going to talk about this for probability, but until then, be safe, and I'll see you around.